Well, physics people, this is the last chapter of the year. What? No, no, no! No, say it's not true! I'm sorry, it is indeed the last chapter. Oh. It had to come eventually. Goodbye. Chapter 17. I'm going to be skipping a number of parts of this to save some time and to avoid the possibility of boring you. So just hitting the basic concepts of chapter 17. Let's see if we can do this in one video. Here we go. First of all, what is evaporation? This whole chapter 17, is about change of phase. There are a lot of fascinating concepts in here regarding the atmosphere and regarding all kinds of things, pigs and dogs and stuff, and canteens. I would suggest you read the chapter for your own edification, but we will be skipping over many concepts here. What is evaporation? As the word implies, right here, evaporation is when a liquid changes phase and becomes a vapor. A vapor. It evaporates, becomes a vapor, otherwise known as a gas. And we call it evaporation when that happens at the surface. Can such things happen below the surface? Yes. We call that boiling. This is not boiling. This occurs at the surface. It is evaporation. Now, evaporation is a cooling process. Why is it a cooling process? All right, imagine that you've got, say, a pot of water, and it is evaporating. What's going on is you have molecules inside here that are all bebopping around, banging on each other, rubbing around each other, and just moving around randomly all the time. The ones at the surface, once in a while, a molecule at the surface will get banged on by one of its neighbors from below with enough force that it pushes it out. Remember that all these molecules are being held in place or being attracted to each other. We have that surface tension thing going on. But sometimes a surface molecule will get banged by one of its neighbors, perhaps some neighbor who didn't like that particular molecule very much, and goes bam, and this guy goes flying out here. Well, it's evaporating. Now, why is it a cooling process? Well, these guys are all moving at a particular average kinetic energy. When a fast-moving molecule hits this guy and knocks him out, this guy just gained kinetic energy, while the guy that hit him loses some kinetic energy. The guy doing the hitting gets slowed down, the guy being hit speeds up. So the guy left behind is at a lower kinetic energy, and when this happens to enough molecules at the surface, the guys here at the surface are all getting slowed down because they are going bam and knocking their friends out, and that slows them down. So it cools the liquid. The average kinetic energy of the molecules in the liquid is going down as they're throwing their neighbors out at high speed. That's the purpose, by the way, of perspiration. Why do you sweat? The purpose of sweat is for evaporation. Hot day, your skin gets all wet. What's going on? Your body is secreting, can't think of the word, sweat. I've lost the word. Yeah, it's sweating. You're secreting sweat, perspiration. Okay, there we go, it's right on the board. And as that evaporates, it's taking away the heat of your body. It cools your skin as the liquid evaporates off your skin. On a really hot, humid day, when you have sweat actually dropping off your nose, well, those droplets of sweat that are falling off your nose, they're carrying with them some of the heat of your body, and it's helping a little bit, but they're not evaporating. So when you're sweating so much that it's actually dripping off of you, that is not as effective as when it's able to stay there and evaporate. Hey, alcohol. Alcohol is really good at vaporizing. It vaporizes very easily. Have you ever noticed if you have a wet paper towel or a paper towel soaked in alcohol, the one soaked in alcohol dries out very quickly, while the one soaked in water stays wet for quite a while? It's because alcohol vaporizes very fast, which is why when you get some, Mr. Beer, don't waste that. That's worth a lot nowadays. It's all right. I just took a little bit. That's why alcohol on the skin feels so cool, because it's vaporizing very rapidly, taking the heat off your body. When I was a kid, I remember if I had a fever, my mom would take a sponge, soak it in rubbing alcohol, and rub it all over me to cool my body and try to bring down my fever. So sweating is a cooling process. Any kind of evaporation is a cooling process. There are some folks who are unable to sweat. They have a genetic problem. They physically are unable to sweat, and they are in danger of death if they overheat. And they have to be very careful to not allow their bodies to get overheated, because they cannot sweat and they cannot get that extra body heat to leave their bodies. More about that a little bit later. Let's move on to what we got here. Yeah, that's why alcohol feels so cool. Oh, the drinking bird. Do you know about the drinking bird? Yes, this drinking bird has a problem with... no, not really. The drinking bird did not get a chance earlier to say goodbye. Oh, I'm sorry, this is not actually the drinking bird. This is the screaming bird, and he just said goodbye. But here is the drinking bird. You've seen these things before. The drinking bird will sit here and do this. Let's watch him for a moment. Watch him in silence here for a moment. No, I don't like silence in videos, so I'll babble while he thinks about taking another drink. Here he goes. Oh, there. Ah, it's so good. And if we watch him for a fairly short time, you know what happens next. You've probably seen the drinking bird before. If you haven't, well, now you see him. He's well known. You can get these at various places, get them online for probably about $10 or so, I'm guessing. I'm not sure. I also saw in a catalog a giant version, about like this tall of one. Pretty cool. I'm not going to buy one, but they're pretty cool. Oh, here he goes. He's going for another drink. And there he goes. How long will he continue to do that? He will do that like forever, as long as there's enough water in this glass for his beak to touch. What's going on? Let's make a long story short. To some degree, it's a bit of a mystery to me. I just read the description in the book of how he works. You can read it for yourself. But long story short, when he dips his beak in the water, his furry little head, and you can't see the fur, but his head is kind of furry. His fuzzy, furry little head is absorbing the water, which is evaporating. As that water evaporates off of his head, it causes the pressure inside his head to be lowered. As the pressure inside his head is lowered due to the cooling of the evaporation, and as the liquid down in here is vaporizing at natural room temperature, the pressure down here is pushing the liquid up the tube. When enough liquid goes up the tube to make his head too heavy, he finally goes clunk. Then the water runs down the tube back to the bottom of his body again, and the process starts all over again. And he will continue doing that as long as his head is able to evaporate water. And that depends on there being water in the glass. I had him going once over the weekend. He did just fine. The water level drops a little bit due to its own evaporation, but he ran like this nonstop for the entire weekend. And he would go longer if I allowed him to. The drinking bird, the famous drinking bird. All right, let's see. Moving on. We'll kind of leave him off on the side here just to, if you get bored of listening to me, you can instead get bored by watching the bird drink. Move him back here like this. Now my goal is to not bump him and spill water all over the place. Okay, let's see. Next screen. Condensation. Well, condensation is nothing more than the opposite of evaporation. There's moisture in the air, water vapor in the air. Every now and then, a molecule of water vapor will be flying around and it will hit my skin, collide with my skin, and stick. And it's clearly losing its kinetic energy. Where is its kinetic energy going? It's going into my skin. It's causing me to warm up a little bit. Condensation is a warming process. As the fast-moving molecules in the air hit my skin and stick, they lose their kinetic energy and transfer it, causing the molecules in my body to move faster, and it's a warming process. So there's this constant battle going on with our bodies. All the time we are both evaporating, liquid is leaving our skin, but at the same time there is condensation of moisture in the air hitting our skin. So if we have more moisture evaporating than we have condensing, then we feel cool. But if we have more condensing than evaporating, then we feel hot, muggy, sticky. So on a very humid day, that means there's a lot of moisture in the air. A lot of moisture able to condense on my skin. And there's going to be less evaporation because there's less, well, say, room in the air for moisture to go out into it. So we have decreased evaporation and increased condensation, and the result is we feel like miserable. Our bodies are not able to cool themselves off as well. You take the same temperature day and go to where my daughter is right now in Eloy, Arizona, in the middle of the desert at a Christian youth camp. Why a Christian youth camp in the middle of the desert? Well, they're near Phoenix, and they minister to underprivileged kids in the city of Phoenix. But anyway, out there in Arizona, the air is very, very dry. That's what a desert is. The air is very dry. So there's very little condensation of moisture coming onto the skin, but there's plenty of evaporation. So the same temperature day in Arizona doesn't feel nearly so oppressive as the same temperature day here in the Washington area that's known for its high humidity. It's all about condensation versus evaporation. Moving on. Let's see, yes, so condensation is a warming process. We've been through that. How about boiling? Boiling is pretty cool. They say a watch pot never boils. Well, not true. A pot of water that's getting ready to boil can be a fascinating thing to watch. Totally off topic here for a moment. Totally off topic. I have observed that if you have a pot of water and it's just starting to think about boiling, getting little bubbles here on the bottom, some of which will try to break off and rise, others stay at the bottom. Some will grow and then shrink and grow and then shrink. And you see these bubbles trying to form. As you watch that, do this sometime. Look intently into that pot of water. In a way that I have a difficult time describing, you'll see kind of a line across here. A line where the refraction of the light changes, and you see kind of a layer. It's hard to describe. You have to see it to understand. But you'll see this line across here. And as the water gets closer and closer to boiling, the cool thing is that line begins to rise. It's just one line. Don't misunderstand here. It is one line. But that line, that line will begin to rise. You can clearly see it. And it rises and rises and rises, and the moment that line hits the surface, the water begins to boil. It's pretty cool. I've never seen that in any textbooks. I've never heard any explanation of that. I've never heard it referred to, but I've seen it. It's real. Check it out yourself sometime. Pretty cool. But that doesn't answer the basic question. What's going on with boiling? You heat up the water. Oh, I didn't put a flame down here. I forgot to put flames. Can I add flames here now? That's kind of pitiful. Oh, I'm lousy at making nice symmetric flames. Okay, so this is my burner. I'm heating up this water. Water here in contact with the pan reaches the boiling point, and a little bubble of vaporized water will form. But there's a problem going on here. You've got increased pressure inside the bubble trying to push out, but you also have the water pressure pushing in. And you've got atmospheric pressure here pushing down. So you've got this battle going on between with atmospheric pressure combined with water pressure, battling against the internal pressure of the vaporized water, the gas inside the bubble. Well, it takes a while for this to really get going because for quite a while the atmosphere and the water pressure win. And if you watch carefully, you'll see bubbles at the bottom kind of grow and then shrink. Another one will grow and shrink. They grow, but as they grow, they're in contact with cooler water up here, and that cooler water causes them to once again condense, and they go back again, and they grow and they shrink, and they grow and they shrink. Once in a while, one might grow big enough to break loose, but it still might shrink on its way up as it passes through cooler water above. Well, that continues until the entire pot of water reaches the famous 212 degrees Fahrenheit or 100 Celsius, at which point the bubbles then rise and go to the top and burst, pop, and you have what we call boiling. But for the water to boil, the whole thing has to hit 212 degrees. Until then, those bubbles are not going to make it to the top. Yes, water is indeed vaporizing, but the atmosphere and the water pressure win until you hit 212 degrees. What happens, by the way, if you lessen or remove the air pressure? How could you manage to lessen the air pressure? How about if you simply go someplace like Denver? Mile-high city, less air pressure up there. If the air pressure is less, it's going to be easier to boil this water. There's not as much competition against the internal bubble pressure. There's less pressure trying to squash it back again. So the water will boil. In fact, water that normally boils at 100 degrees Celsius, in Denver, it boils at 95 degrees Celsius. That can present some problems. You're cooking your spaghetti. It's not the boiling process that cooks your spaghetti. It's the hot water. It's that 212 Fahrenheit water. It's that 100 degrees Celsius water that's cooking the spaghetti. So what happens in Denver? In Denver, your water hits 95 degrees and it's boiling. It won't go past 95 degrees. Instead, it releases its energy by boiling. So your spaghetti is only cooking in 95 degree water. What's the result of that? It's going to take a little longer because the water's not as hot. That's also the purpose of a pressure cooker. Exactly the opposite of going to Denver. A pressure cooker puts a lid across this thing so that as the water vaporizes, it can't get out. It's going to build up pressure and pressure and pressure and more internal pressure and more pressure as the water boils, and eventually this whole thing is going to kaboom, explode. That's not a good thing. It's not a good thing at all. So what do they do to keep that from happening? There's a little hole up here. A little tube that sticks up here. That little tube lets the pressure escape. Well, then what good is that? Well, it wouldn't be any good at all, except for the fact that you then put this heavy little metal thing on top. It doesn't seal, it just kind of sits there. It's heavy and it just sits there. It's able to move around. It's weighted just right so that it only lets the gas escape when it hits a certain pressure. Before that point, the weight alone of this thing keeps the hole sealed. It allows the pressure inside to increase to a certain degree, but not too much, because they don't want your pressure cooker exploding. That's why this thing on top wobbles around, and you can hear it going click, 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 and you see the steam coming out, because the pressure inside has reached a point where it can lift this thing off of that tube a tiny bit and let the pressure out. What if that tube gets clogged? What if a piece of meat gets up in there and clogs the tube? Oh no, it's going to explode! That's why over here someplace they have this little rubber plug. That's an emergency relief valve. If this for some reason gets clogged up so the pressure can't get out, then it'll reach a certain point where it'll blow that little rubber stopper thing ching, out of there and let the pressure out. So your pressure cooker is quite safe to operate. But if you were to seal this somehow and seal this also and then put it on the stove, well, don't do that. I saw a YouTube video once, maybe it was Mythbusters or somebody, where they took a hot water heater and they rigged it so that it couldn't vent if it overheated. Yes, your water heater in the basement has an emergency relief valve in it. If the pressure builds up too much, it'll let the water come out instead of exploding. Well, they did an experiment to see what would happen if you had a hot water heater that did not release the pressure. Dramatic. They built a little miniature house using the same construction methods where you would build a real house. And that thing flew from the basement right through a couple of floors of the house and through the roof. And how high it went, I do not know. But it went kaboom and took off like a rocket. Yeah, you don't want your hot water heater to explode. So it has a relief valve built into it, just like the pressure cooker. All right, let's see what's next here. Oh yeah, pressure cooking. Okay, yes, we've talked about that. Good. Boiling is a cooling process because boiling, as those water vapor bubbles expand and rise, they're taking with them energy. The energy that went into making the water vaporize is then being released, which causes the liquid left behind to cool off. Well, then why does it stay at 212 degrees? Because we're continuing to apply heat. Let's go back here for just a moment. Once it reaches 212, we continue putting heat into it, but every bit of heat that we put in down here is being released up here as water vapor, as those bubbles rise and burst and send their energy, their water vapor, into the air. So just as much energy is being released into the air as is being put in down here. So it stays at 212 degrees. As long as you have the heat applied, and as long as you don't seal it or something, it'll stay at 212 degrees. Did I mention to you, back in the pressure cooker, I'm not sure I mentioned a very important detail of why a pressure cooker cooks food fast. Details. Because you're increasing the pressure inside here, you're also increasing the boiling point. I don't know what temperature the water can get to, but when it's pressurized, the water temperature inside that thing goes way above 212 degrees. That's the beauty of a pressure cooker. It's not the pressure that cooks the food. It's the higher temperature water that cooks the food. Pretty cool concept. I don't know, the pressure may have something to do with it also, but it's mostly just the fact that you're able to get the water higher, way higher than 212 degrees. Okay, other things come to mind like nuclear power plants and how they use pressurized water in their cooling systems, and cars. The coolant inside your car engine is pressurized somewhere beyond normal pressure, using a special cap on the radiator that regulates the pressure inside, and all kinds of examples like that we just don't have time for. Okay, let's see. So that's why boiling water stays at 100 Celsius or 212 Fahrenheit, yes. Change of phase. This might be our last concept here, is it? Almost. Change of phase. Let's consider for a moment 1 gram of water. What's 1 gram of water look like? 1 gram of water is 1 cubic centimeter. It's about, if I draw a little cube, it's about that much water right there in there. That's about 1 gram of water. Okay, you know what a calorie is, I hope. A calorie, little c calorie, not a big C calorie, but a little c calorie is the amount of heat required to raise 1 gram of water by 1 degree Celsius. It's not very much heat. Okay, now, let's start with 1 gram of ice, right there. 1 gram of ice. Let's suppose that ice is at negative 10 degrees Celsius. All right, let's put some heat into it. A little bit of heat. The temperature rises to negative 9. A little more heat, it goes to negative 8. A little more heat, negative 7. A little more heat, negative 6, negative 5, negative 4, negative 3, negative 2. Put a little more heat, we get negative 1. Put a little more heat, it rises to 0. Put a little more heat, it stays at 0. Put a little more heat, it stays at 0. Put a little more heat, it stays at 0. Put a little more heat, it stays at 0. Put a little more heat, it stays at 0. Put a little more heat, it's stuck. The ice is beginning to melt, but its temperature stays at 0 even as you are putting more heat into it. Because the heat you're putting into it is not going to raise its temperature, but it's going to break up those crystals that have formed to make it become solid ice. So you put in more and more and more and more and more and more heat. Yes, the ice begins to melt, but it does not change temperature. It is stuck at 0 degrees. How long does that go on? It'll stay at 0 degrees until you've put in 80 calories of heat energy. Enough energy to raise a gram of water by 80 degrees. It doesn't raise it, but it's enough to normally raise it by 80 degrees. You put in 80 calories of heat energy into that 0 degree water, and then finally all of the water will melt. And once all the water is melted, then and only then you put in that 81st calorie, and the temperature will go from 0 to 1. Put another calorie, 1 to 2. Another calorie, 2 to 3. Everything goes back to normal. So there's that weird point when it hits 0 degrees. That doesn't mean instant melting. No. When it rises up to 0 degrees, you've got to put in an additional 80 calories per gram to melt the whole thing so that it can once again start to rise in temperature as you put in more calories. Pretty cool. Now what happens at the next change of phase? What happens when you have all liquid now, and suppose the liquid is now at the same 1 gram of water, but it's now liquid water, and suppose we're now at 95 degrees Celsius. We put another calorie of heat, it goes to 96. Another calorie, it goes to 97. Another calorie goes to 98, then 99, then 100. Put another calorie in, it stays at 100. Put another calorie in, it stays at 100. Put another calorie in, it stays at 100. Get this. It takes 80 calories per gram to melt ice. But once that water hits 100 Celsius, you have to pump in a whopping 540 calories of heat to raise that silly little gram of water, to get that silly little gram of water to actually completely evaporate. Once it evaporates, then you put in another calorie and the temperature of that vapor will rise. You put in more heat, it rises. Put in more heat, the temperature rises. Put in more heat, temperature. But when the water first hits 100 degrees, it will stay at 100 until you put in 540 calories per gram of water to finally get the whole thing to evaporate, and then, and only then, does its temperature once again begin to rise. It's stuck at 100 degrees, which is pretty bizarre. Now, what does that tell you? That tells you that steam, because it took 540 calories per gram to get that 100-degree water to vaporize, it tells you that steam contains a vast amount of energy. Have you ever been burned by steam? Oh, I have. I mean, I've learned to try to avoid it, but sometimes I make mistakes. Just today I had, I don't have it's way over there, the empty bowl, but I had one of these microwavable Dinty Moore beef stew thingies. And I have learned that after you heat that thing up in the microwave, you want to peel back that film very carefully, Because if you don't watch what you're doing, as you peel it back, the steam will hit your knuckles and it hurts. I mean, you can actually get burned. Steam is very powerful. I could give you a zillion examples of instances where steam has been very painful. Even a hot oven. You open the door and you're blasted by two things. You're blasted by hot air, but if there happens to be a lot of water vapor because you've been baking something really juicy and wet, that steam will come up in your face also, and that can be really bad. I've had the bad experience of getting my hand over top. We have these pots at home that they're not pressure cookers, but they do have a vent in the lid. And when that thing gets going and the air, the steam shoots out that little vent, if you put your hand over that, and you will regret it. Steam, water vapor, contains a huge amount of energy. Steam contains a vast amount of energy. There we go, yes. So a couple of terms here that you need to be aware of. Latent heat of fusion. That's what we call the amount of